Hereby I open this academic ceremony at Maastricht University. First of all, I welcome Mr. Alexandru Florea, and he will defend his thesis, which is titled Sodium 18F Fluoride Positron Emission Tomography for non-invasive identification of micro-calcifications as marker of atherosclerotic plaque vulnerability. And he will defend his thesis in the framework of a double doctorate of the RWTH Aachen University and Maastricht University. Welcome all members of the degree committee, and in particular the 4 supervisors who are sitting just here in front of me. Professor Felix Montargis, he is professor of nuclear medicine at RWTH Aachen University and Maastricht University. Professor Eline Kooi, she is professor of medical physics, in particular vascular imaging at Maastricht University. Professor Leon Schurgers, he is professor of biochemistry of vascular calcification at Maastricht University. And the 4th supervisor is Professor Bucerius, he is professor of nuclear medicine at the University of Medicine in Göttingen in Germany. I will introduce the 6 opponents later during the ceremony, and I would like to welcome you here in the aula, and I welcome all the followers of the live stream. Mr. Florea, may I ask you to give a summary of your thesis, and I wish you lots of success in the coming hour. The floor is yours.
Thank you, Prorector, for the nice introduction. Dear family, dear colleagues, dear friends, dear online guests, please allow me in what follows to present a summary of my thesis entitled Sodium Fluoride Positron Emission Tomography for the non-invasive identification of micro-calcifications as markers for atherosclerotic plaque vulnerability. However, first, I would like to start with a story. Usually, during the summertime, I like to go to work using a bike. However, on the 13th of July last year, I had an unfortunate bicycle accident during which I injured my knee. Immediately after the accident, I tried to walk. However, I saw that I couldn't, so I knew immediately that I managed to broke one of the ligaments in my knee. Indeed, you can see on my MRI here that one of the ligaments is actually missing. And just like that, my life changed within the split of a second. I needed to wear crutches, and a race against time started as my knee started to become stiff and fibrotic. However, why would my knee even start to become fibrotic? Well, this has to do with how our body treats any type of injury, actually. Initially, an inflammation is started, which will clear up the damage caused by the injury, and then it will pave the way for healing. And healing can be either via complete tissue regeneration, where the tissue is completely regenerated and it is indistinguishable as it was before the accident. However, in our adult life, tissue regeneration is always accompanied by tissue repair. And tissue repair also comes in 2 flavors, fibrosis and calcification. You can think of fibrosis and calcification as one is some rubber bands put together, giving the tissue a little bit of elasticity, and calcification, you can think of it as a brick wall, separating what it is inside from what it is outside. And I wanted to tell you this story as inflammation and calcifications are important aspects within my PhD thesis. But yet still, what this has to do a bike accident with atherosclerosis, the focus of my PhD? Well, I can imagine that everybody knows what happened during my bike accident. My knee simply broke. But what is atherosclerosis? As the definition of this disease is pretty complex, I'd like to start by saying atherosclerosis is the cause of almost 70% of cardiovascular disease. And if you go on the website of the World Health Organization, you're in the subsection cardiovascular diseases, you're going to come across this sentence. An estimated 17.9 million people died of cardiovascular disease in 2019, representing 32% of all global deaths. Of these deaths, 85% were due to heart attack and stroke. In chapter 1 of my thesis, I explain how atherosclerosis is actually the #1 killer in the world. Moreover, this single disease is attacking 2 of our most vital organs, the heart and the brain. Today, for time's sake, I will describe the heart attack. Well, what happens during a heart attack is that a seemingly healthy heart with healthy vessels, at one point, one of the vessels becomes clogged and the tissue afterwards starts to die. The patient feels an intense pain, an intense chest pain, and might even faint, and it needs to go to the hospital quickly. And the life of this patient change in the split of a second. However, what caused this acute cause of events? Well, for this, we need to go back in time and to look into the vessel that caused this event and look into the vessel wall. In chapter 1 and also in chapter 2 of my thesis, I explain how everything starts with a single lipid droplet, which initially floats around the blood, and at one point, because of several medical reasons, it gets entrapped inside the vessel wall. And when there is one lipid droplet, there are many more different lipid droplets which flow around the blood, and then they get entrapped inside the vessel wall. And how does our body treat these lipid droplets that are inside the vessel wall? As an injury. And now you know that after an injury, inflammation comes. And for some yet unknown reason, our body goes after the inflammation with calcification. In order, as these calcifications inside the vessel wall are incredibly small, they bear the name micro-calcification, in order to emphasize how small they are. And from this stage, only time needs to pass. And as the lipid droplets become more and more, they accumulate more and more, inflammation becomes more pronounced, and also microcalcifications become more and more. And at one point, this plaque is called to be vulnerable for rupture. And when the rupture happens, and also the heart attack happens. If the patient gets in time to the hospital, there's also life after a heart attack. And usually, after this stage, the calcifications become so intense, these microcalcifications become so intense that in order to distinguish those calcifications from what comes later, they bear the name macrocalcification. And actually, this is the stage where we are, where the medical imaging capabilities can detect. We can see microcalcifications. However, as you can see from this diagram, this is already too late. Ideally, we would try to image microcalcifications in order to prevent the acute event and to foresee it. In chapter 1 and also in chapter 2 of my thesis, I explain how inflammation and microcalcification make for suitable processes to be imaged during atherosclerosis. And also in chapter 2, I explain how inflammation creates microcalcification. However, also in return, microcalcification is a trigger for inflammation. You can think of this as having a very small stone in the wheel of your vehicle. With every turn of the wheel, the stone will get deeper and deeper, and in the long run is going to damage the thread, and you're going to have a flat tire. Therefore, within my PhD, we also looked for suitable targets for inflammation and also for microcalcification. That's how we came up with sodium fluoride to detect hydroxyapatite. Sodium fluoride, this two-atom molecule, is able to specifically bind to hydroxyapatite, the very building block of microcalcification and calcification altogether. In the case of inflammation, we went with a CXCR4 addressing tracer that specifically binds to the CXCR4 marker on inflammatory cells. This is already a known marker for inflammation. In chapter 3 of my thesis, I present how we imaged microcalcification using an atherosclerotic mouse model. Within this model, we developed several stages of disease. A group of animals developed advanced stage atherosclerosis, while another group developed early stage atherosclerosis. And we also had one group as control that did not develop any kind of plaques. Initially, we scanned these animals using the CT. However, we could not see any plaques in their heart region. Then, the surprise came when we injected these animals with sodium fluoride. As you can see also here, in the advanced stage animals, there is an intense uptake in the heart region of sodium fluoride, suggesting that these animals have microcalcifications inside their heart region. And also this was the case of the early stage. Here we also were able to see a specific sodium fluoride uptake inside the heart region. However, in the case of the control animals, there was no sodium fluoride uptake in the heart region. In chapter 5 of my thesis, I present how we use the same atherosclerotic mouse model to image inflammation. Also, for these animals, on the CT, we saw no plaques. However, when we injected the CXCR4 addressing tracer, again, in the advanced stage animals, we were able to see an intense CXCR4 addressing tracer uptake, and also in the case of the early stage. However, in the case of the control animals, we saw no uptake. Therefore, we concluded that these two tracers can be used to image early atherosclerosis. So, coming back to imaging of atherosclerosis, according to this data, we were able to say that we can detect early stage atherosclerosis using the radioactive tracers, sodium fluoride, and also the CXCR4 addressing tracer. And what would mean for my bicycle accident? Well, it would mean that, that on the day of my accident, before the accident, we'll be able to tell me, stop. If you go further along this line, you're going to have an accident. However, we would not be able to prevent the accident itself. So next, we also looked in the treatment of atherosclerosis and realized that patients actually receive a treatment against the risk factors for cardiovascular disease. And this means that from the processes that we learned that happens inside the vessel wall, so micro-calcification, the lipid droplet, and also the inflammation, there are good available clinical drugs that, that can combat both the lipid droplet and also the inflammation process. And then therefore, these processes can be combated with. However, micro-calcification would still remain. Therefore, in chapter 2 of my thesis, we also looked in possible treatments for microcalcification. And here, I also describe why we consider vitamin K as a cost-effective treatment against microcalcification. As it is usually in research, when we want to see the influence of a compound, then we also look for the influence, what happens inside a body when this compound is completely missing. This is why we're also interested to see the action of a vitamin K antagonist that can block the action of vitamin K. So we used warfarin, a specific blocker for vitamin K. However, warfarin was created as a mouse and rat poison, and given warfarin alone to mice, it will make them bleed to death. However, we looked into the literature, and giving a little bit of vitamin K1, which specifically acts on the liver, it will inhibit the lethal bleedings, but still enable the warfarin to block the action of vitamin K inside the vessel wall. And this is what we did. In chapter 3 of my thesis, I present the results from these animals. And from the initial first PET scan, something struck my eye. This spotty uptake inside the heart region, which also correlated with a spotty calcification on the CT of these animals. Something even more interesting came up when I looked at the vessels of these animals under the microscope. I'm talking about this intensely stained region, as this region correlated with the spotty calcification on the CT and also with the spotty calcification, spotty uptake on the PET, I decided to stain this region for a specific staining of calcification. And indeed, here was calcification. Therefore, we concluded that blocking the action of vitamin K increases the calcification inside the vessel wall of these animals. Now, we were really interested to see what happens if we treat these animals with vitamin K2, a vitamin that acts specifically on the vessel wall. To the surprise of all of us, the vitamin K2 treated animals showed no sodium fluoride uptake inside their heart region. Actually, there was no statistically significant difference between the control animals and the vitamin K2 treated animals. And then, therefore, as the results from this preclinical mouse model was so interesting, we decided to also propose a clinical trial. And therefore, in chapter 4 of my thesis, we proposed the INTRICATE study, which is a clinical trial where patients with atherosclerosis would receive a vitamin K2 treatment, and before the start of this treatment and also at the end of this treatment, they would receive a sodium fluoride PET MRI in order to see the influence of vitamin K2 on their vascular calcification. So, finally, in the end, coming back to imaging of atherosclerosis and also to my bike accident, then according to this new data, we propose that by giving a vitamin K2 supplementation, we'll be able to avoid the acute event because of inhibiting the vascular microcalcification. And in the case of my bicycle accident, this would mean that we'll finally be able to remove the obstacle from the way and safely guide me home. My PhD thesis concludes that we are able to detect early stage atherosclerosis using radioactive tracers such as sodium fluoride and also the CXCR4 addressing tracer, and also that vitamin K2 seems to reduce the cardiovascular burden created by micro-calcifications. Therefore, we also say that the next logical step is the evaluation of vitamin K2 treatment in a human trial. Lastly, I'd also like to acknowledge the date of the day, the 8th of March, and wish all the women in the audience a happy Women's Day. Thank you all for your attention, and now I give back the word to the Prorector.
Thank you very much for the clear presentation of your thesis. The opposition will now be opened by the chair of the Thesis Assessment Committee, Professor Chris Reutlingsberger, and he's Professor of Biochemistry of Apoptosis at Maastricht University. Professor Reutlingsberger.
Thank you, Mr. Prorector. Dear candidate, I want to start with giving my compliments to you and your promotion team with this work, which I read with much of interest. And I listened to your presentation, which was, to my opinion, very clear. And you mentioned in your presentation that you studied micro-calcification, but you also mentioned macro-calcification, and you mentioned spotty calcification. And in your thesis, you define micro and macro calcification based on size. So it's below 50 micrometer and above 50 micrometer. Mm-hmm. But what is the definition of spotty calcification? Can you give that?
Yes. Thank you, highly esteemed opponent, for this question. Spotty calcification is it's a term used by the radiologist to define concentrated calcification on the CT. So spotty calcification, it's mostly a term used by radiologists when analyzing CT data, and also I think also on MRI data.
Yeah, and you write in your thesis that there is an association between the characteristics of the plaque, the risk of rupture, the vulnerability, mm-hmm. and macro calcification, which is protecting, you say, and micro, which is enhancing the risk. And what does spotty do then? How is that associated?
Yes, as spotty calcifications are calcifications that can be seen on the CT, then this means that they are also a sort of macro calcification. However, as the name suggests, they are only localized in one spot, and usually when the term macro calcification is used, is more or less like a plaque. Okay. So in a more advanced stage of spotty calcifications.
Now getting to your imaging tool, the PET and the sodium fluoride, mm-hmm. When you make the image, you analyze the data and you use voxels to analyze that. And when I calculate it, then the volume of a microcrystal, according to your definition, is 300 times less than the volume of the voxel. Mm-hmm. So what do you pick up with the PET?
Indeed, thank you very much for this challenging question. This is the benefit of using sodium fluoride. Sodium fluoride is able to bind to hydroxyapatite crystals. However, it's not able to penetrate the crystal itself. Actually, if we would have a macrocalcification and image it using sodium fluoride, we would see a necrotic core inside the middle, as the sodium fluoride is not able to penetrate it.
But does that stick to your definition of size? So is there an abrupt border at 50 micrometer?
For this, I'm not exactly sure, but we defined also the term microcalcification based on the immunohistology of these animals, and this is why on the advanced stage animals we used.
So what I really want to know is, do you pick up microcalcification? Because the microcalcification that has the size of a cell or mm-hmm. even less than a cell. And the microcalcification, that is, I think, the foremost researcher was Vermani, who showed that the culprit plaques contained these small crystals, but that was after the patient died. Mm-hmm. And so do you pick up really the micro-calcification, and can you then see that the plaque is vulnerable, or predict that the plaque is vulnerable?
Using sodium fluoride, we are able to do this, as microcalcification is usually a lot of calcifications spread out together, and then when sodium fluoride is used as an imaging tool, this entire area, which does not have the required attenuation to attenuate the CT, then it sees completely, it lights up on the PET. So we are not able to indeed see the individual microcalcifications. However, we're able to see this region contains microcalcifications as it has sodium fluoride. However, nothing on the CT.
Yeah, and your mouse data of chapter 3 are very intriguing, and I think they warrant the design of a study that you mentioned in chapter 4. Now let's go to the design of the study. There, I don't see, and that wonders me, I don't see an inclusion criteria based on the range of body mass index. And it wonders me because you intend to give a single dose to these patients, not based on body weight.
Yeah.
And both vitamins are fat soluble. Mm-hmm. So the body weight will impact bio uptake, bio availability, biodistribution, and bioavailability. So why did you choose not to use this as an inclusion criterion?
Yes, thank you for this interesting question. We decided to use the dose that is also used usually in other clinical trials, so that our data would be comparable with other clinical trials. And in most clinical trials that at least I read, then they use a similar dose of vitamin K2 supplementation.
Okay. And now a really challenging one, if I have time. Do I still have time? You do. And that is, you want to see the effect of vitamin K on the size or the amount of sodium fluoride uptake, hypothesizing that vitamin K slows down the progression of calcification, and maybe even reverses calcification. Now, let's assume that will happen, and your vitamin K will reduce calcium crystals into the sub 50 micrometer size. So they become really microcrystals and then make the plaque vulnerable. Is that a good choice for a therapy then? A dietary therapy?
You may give a short answer.
Yes,
that's
indeed.
A challenging one.
Yes, it's a challenging question. Indeed, it might be that at one point it will not be good for the patient. However, our intent is actually to introduce vitamin K supplementation for a longer period, and then therefore completely halting the microcalcification from the macro. Yeah.
Thank you. I'm very satisfied. I give the word back to the pro-rector.
Thank you, Professor Reutlingsberger. The next opponent is Professor Olivier Gijsens. He is Professor of Nuclear Medicine at the University Clinics St. Luc and the Faculty of Medicine of the Catholic University of Louvain in Brussels, Belgium. Professor Gijsens.
Thank you, Pro-Rector. Dear candidate, thank you very much for this very nice presentation. I also read with a lot of interest your thesis, and I would like to congratulate you and your promoters on the extensive work you've been doing. I would like to start a discussion with a question on chapter 5 on CXCR4 targeted imaging. You nicely showed in your preclinical animal model that you were able to detect a signal, a PET signal, assuming coming from CXCR4. But I would actually like to know which subpopulation of cells we are actually targeting in the context of an atherosclerotic plaque.
Highly esteemed opponent, thank you for the question. CXCR4, according to literature, is mostly expressed on macrophages, however, also on other antigen-presenting cells. So at the stage when I wrote the thesis, as that chapter is not yet published, we only considered that yes, we're going to see CXCR4 positive cells inside a plaque. However, in the meantime, we're also performing immunohistostainings on the plaques from these animals in order to indeed identify which CXCR4 positive cells are we seeing there.
Okay, so you don't have
we
an
don't
idea at this moment which
So,
cells you mainly target?
A concrete idea, no. I cannot give an exact answer. However, based on literature, I'm expecting mostly macrophages to be targeted.
Okay, thank you. So your goal with CXCR4 is actually a tracer for inflammation. So why not using FDG, which is an established tracer for inflammation? Do you think that CXCR4 is more specific than FDG in this setting?
Indeed, CXCR4 would be more specific for imaging inflammation, and additionally, when translating our preclinical data into the human scenario, the FDG has the disadvantage that is also taken up by the heart muscle, and then also there is pretty difficult to identify inflamed plaques, as also the heart muscle has FDG uptake. However, using CXCR4, so the gallium pentixaphore, then we would be able to also image the inflamed plaques in the heart.
I just want to pick in that question. There is physiologic uptake of FDG, but are there means to suppress that uptake or to prevent physiological uptake in a myocardium in order to allow visualization of these plaques?
Yes, the patients can also undergo fasting before, and then this will stop, will reduce actually the FDG uptake.
Yeah. And any other potential interventions that we use in routine clinics to further ensure reduction of physiological uptake in the myocardium?
No, I'm afraid I don't know.
Okay. And then the last question on that topic, you decided to use gallium-68.
Mm-hmm.
Would there be any advantage of using a fluorine-18 variant of CXCR4 in a preclinical setting, taking into account the physical properties?
Yes, it would be a definite advantage of using a fluorinated version of pentixaphore, as gallium has a positron range of around 3 millimeters, as far as I know, and this actually increases. Yeah, it increases the volume and also the uncertainty where exactly the plaque would be, especially as you mentioned, in a preclinical setting where the plaques are incredibly small. However, F18 has a positron range of around 1 millimeter, as far as I know, and then this would enable us to more specifically determine where exactly the plaque is.
Okay, thank you. And then I would like to change thoughts about a clinical translation of your tracers. So you state in the book that sodium fluoride has an improved detection of culprit plaques compared to FDG, but you also showed that the earliest hallmark is actually inflammation, and that micro-calcification is a consequence, and you're in a vicious circle. So do you think that there is no role at all for FDG in the workup of patients with atherosclerotic or lesions?
I think FDG is a good tracer at the moment, but I think that the other tracers are going to come that in specific settings are going to replace FDG, and especially as FDG is actually a marker for glucose metabolism, I think that we would need more specific targeting also of the processes inside a plaque in order to know exactly what is happening there.
Okay, and when we take it to the next level, the American Heart Association recommendation states that we should try to have an early identification of subclinical atherosclerotic lesions by CT or carotid ultrasound. Which one of your tracers you tested would you recommend for screening these populations? Do you think one of your tracers can replace ultrasound, coronary CT for these detections?
If we're talking about calcification, and indeed, I think that the sodium fluoride is able to would be able to replace the CT and detecting earlier stages of micro-calcification, and also in terms of the ultrasound, also for the carotid plaques. Yes, I do think so.
Okay, thank you very much. I give the word back to the prorector.
Thank you, Professor Gijsens. The opposition will be continued by Professor Fabian Kiesling. He is not present here, but he is present online, and you can see him on the screen. He is Professor of Experimental Molecular Imaging at RWTH Aachen University in Germany. Professor Kiesling.
Thank you very much for the kind introduction. Dear candidate, first of all, I would also like to congratulate you to the appealing work that you did for your thesis. And I would like to continue asking you a little bit more about the clinical perspective and implementation of your approaches. So the problem with early plaque detection is that usually these patients are not symptomatic. That means we are talking here about a screening approach, and screening means you will scan a really large population. My first question is, do you really think that PET and SPECT are suitable for that purpose? Because I once talked to someone from industry and he said even contrast-enhanced imaging in any imaging modality would not suit for screening purposes because of costs and risk of side effects already due to injection of probes and so on.
For your question. Yes, however, also as I mentioned in the beginning, atherosclerosis is the #1 killer as a disease. Actually, this disease is killing more people per year than the entire population, than the entire cancer entity. People that die from cancer, I think in 2020 they were around 9 million people, and as I mentioned also in my introduction, in 2019, because of cardiovascular disease, more than double people died. I think that early screening would be important, especially also when we come up with such an elegant solution of vitamin supplementation, if indeed vitamin K2 supplementation would be able to reduce the micro-calcification burden in these patients. And also this, the imaging of vulnerable plaques would be an important tool also in the case of interventional medicine, to know exactly which plaque to target, and also which plaque to be treated or taken out in the case of carotid artery disease.
Okay, but now taking also a look at the costs. So PET is a very costly imaging modality. It's not broadly available as other imaging modalities. Why didn't you consider to switch to SPECT, for example, which would be cheaper and broader applicable to patients? So you think, why do you think PET is necessary as a screening modality in this regard?
Thank you for this challenging question. I don't necessarily think that PET is specifically required in the clinical scenario. However, taking into consideration that in the case, at least in the case of our devices, the resolution of the preclinical PET was actually better in detecting small amounts of radioactivity as compared to our preclinical SPECT, then we decided to do PET imaging. However, indeed, there would be no issue with switching in the clinical scenario to SPECT, which indeed is cheaper and also achieves a good enough resolution, a spatial resolution, in order to detect microcalcifications, also inflammation in the clinical scenario.
Thank you very much. My next question is related to the therapeutic consequences of the imaging approach. Yeah. So you already mentioned some therapeutic opportunities that we would have. My question is now, why taking that big effort and not just measuring the vitamin K levels in the blood of patients and just generally supplementing vitamin K?
Yes, indeed. We are actually also measuring for these patients. We plan to measure for these patients not the vitamin K blood concentration, however, other markers that show the activity of vitamin K inside the vessel wall. Indeed, measure via these processes, via these investigations, we would be able to see maybe an effect or not. However, we were interested to see the hard fact change in calcification, and as in a clinical trial, we would only be able to do this using imaging.
My question is related to think about population screening. So instead of making, for example, these kind of diagnostic approaches with imaging, you could also say you just measure the vitamin K levels of the patients. If they don't have enough, you supplement it, like it is done, for example, with iodine, where you have in the risk areas, you give the whole population iodinated salts, for example, for their food as a supplement. Or would you then in these patients give really a high dose of vitamin K? Yeah. Because it's also toxic, as you mentioned. Yeah. So would you then, in these early plaque development populations, give a higher dose than is usually present in the normal blood? Or is the problem rather be a lack of vitamin K in the broad population that then leads to atherosclerosis development?
No, so either way, we are planning to do a correlation between the blood samples of these of the patients and the imaging of these patients. And indeed, as you mentioned, also in the discussion of my thesis, I argue actually that as there is no description of over-vitaminosis via vitamin K, then it's then at one point there might be enough literature evidence in order to increase the daily recommended dose of vitamin K, especially in case of vitamin K2. And via this, as you mentioned in the case of iodine, we would have a very simple and elegant prevention method for the entire population.
Thank you. And my last question is a bit on the potential theranostic ability of your probes. Would it be also an idea to, for example, kill the inflamed macrophages in the plaques by using therapeutic radiotracers in combination with vitamin K targeting?
Yes, indeed. This is actually something that I'm thinking too. Especially, we could also use a nanocarrier system that would be on the surface, be labeled with the CXCR4 addressing, with the CXCR4 addressing subunit, and then inside it could also have either, for instance, also why not vitamin K, so that we would be able to deliver vitamin K exactly where it needs to be. So to answer your question, yes, I do not exclude, and I also have thought of this approach.
Thank you very much. I think that's it. What I wanted to ask. Thank you very much, and congratulations again.
Thank you, Professor Kiesling. The next opponent is Dr. Hein Verberne. He is Associate Professor of Cardiovascular Imaging with a focus on atherosclerotic inflammation and myocardial sympathetic activity. And he is affiliated with the Amsterdam University Medical Center. Dr. Verberne.
Thank you very much for the kind introduction. Dear candidate, nice to be here. I was just on time. And speaking about time, the following. You start your thesis with a bold statement, lock and load, firm. This is where we go, this is where we need to aim for, and this is where we aim for, and we get it, and we do it. The only thing what I feel when I read that, it's you could also say too little too late, because calcification is the end of a process. So why focus on the last step of this process? Because as you showed also in your presentation and throughout your thesis, inflammation is key. And it starts with and it ends with, and throughout the process there's inflammation. So why focus on such a specific target instead of the broader aspect?
Esteemed opponent, thank you for your question. Yes, indeed, also using the CXCR4 addressing tracer, or for that matter of fact, any other tracer that is able to target inflammation, we could also use medicine directed against stopping calcification. Stopping inflammation. However, we wanted to look also in a feasible treatment for calcification, as I present in chapter 2 of my thesis. There are not that many clinical available options, let's put it, to treat calcification. And also especially is the problem, for instance, warfarin is also given to a lot of cardiovascular patients, and as I showed in my thesis, and it's also already known in the literature, warfarin actually increases vascular calcification. So this is also one important aspect within the treatment of atherosclerosis. There are several drugs that we're giving to the patients. They're actually increasing their calcification levels. This is why we wanted to look for feasible options to reduce calcification. Indeed, it might seem that we wanted to neglect inflammation. However, this was not our aim. Our aim was only to find a feasible solution also for micro-calcification. As for inflammation, there are clinical available drugs.
Yes, I agree. But if we go back to the question of the previous opponent, he asked the question, how do you want to implement this if you look from a clinical perspective? And then it becomes a little bit problematic, because there is capacity in PET-CT, but the tracer that you have is a readily available tracer, but there are others, more, even maybe a little bit cheaper, like FDG with its problems. Mm-hmm. Why not go for the general aspect? Because this is so specific and it's later on the process, and what you would like to have, you would not like to end up with calcification. You would like to prevent calcification, but once it's there, you cannot treat it. It will be there forever. At least I'm not aware of trials that were able to dissolve calcification. Once it's there, and it remains. So, in a broader perspective, how do you would like to shift or translate the outcome to a clinical perspective? Would you like to have everybody with increased cardiovascular risk factors have a PET with fluoride or with FDG? How do you foresee the future? How do you would like to screen those patients that might be at risk?
Yes, indeed. I'm also not aware of any study that was able to actually, as you mentioned, dissolve calcifications from the vessel wall. I think that sodium fluoride is a good tracer, but it also has, as you mentioned, or maybe inferred only, its limitations. Sodium fluoride is able to see the calcification that it's already created. Ideally, we would try to target, for instance, the vascular smooth muscle cells that are actually the cells that start also the microcalcification process. Within my PhD, we actually looked also into other targeting agents. However, at least in our preclinical scenario, we saw no specific uptake inside the heart region and also the specific regions where the mice develop atherosclerosis. We assessed also COX-2 addressing tracer for inflammation. In the case of calcification, we also labeled phetuin, which is a peptide that is more or less responsible for us right now not having calcified arteries in our bodies. And sadly, as I mentioned, at least within our mouse model, we did not see any specific uptake. However, if we would indeed want to treat microcalcification from the beginning and to completely cure this process within the vessel wall, indeed, sodium fluoride, it's good enough as it is available right now. However, novel tracers would need to be would need to be assessed and also invented, why not, in order to be able to foresee micro-calcification.
Yeah, but then go back and then make the next step, because that was my second part of the question.
Mm-hmm.
How do you foresee in clinical reality to screen patients? How do you foresee it? Because it's in line with the question of the other opponent. How do you foresee that? How do you envision, let's say in 10 years from now, I might be at risk because of my age, whatever risk factors I have, what would you foresee how I should be screened to prevent calcification, or at least to prevent any cardiac event, because this is all related to preventing events. So how do you foresee that? Is there a role for this type of imaging, or is functional or is anatomical imaging with the CT further enhanced? You see some calcification, and we'll come back to what is micro-calcification. So how do you foresee that? It's going to be your clinical future.
Yeah. I think that also the CT and especially also the MRI techniques, they would be able to see also, or maybe better said, to detect early stages also of calcification. And in the case of screening, then this would actually replace the PET. However, where I see the advantage of PET is specifically saying this plaque is at risk, and then this plaque needs to be removed. Or
yeah, but if I have one more question, a little one, small answer is enough. You speak about vulnerability and culprit lesions. In my understanding, there always were two separate entities. Do you agree?
Yes.
Okay. Maybe in the future, I would like you to discriminate those two in your answer a little bit. But thank you very much. I'm very happy with the answers that you have. Thank you.
Thank you, Dr. Verberne. The opposition will be continued by Dr. Ingrid Dijkgraaf, and she is Associate Professor of Biochemistry, in particular Nuclear Molecular Imaging at Maastricht University.
Yes.
Dr. Dijkgraaf.
Thank you, Pro-Rector. Dear candidate, I first would like to congratulate you and your whole promotion team with the completion of your thesis. It was really a joy to read this extensive and multidisciplinary work, so compliments. But when I started reading your thesis, proposition 11 immediately caught my attention. And I would like to ask your paronyms, one of your paronyms, to read proposition number 11.
Proposition 11. We have enslaved the rest of the animal creation and have treated our distant cousins in fur and feathers so badly that beyond doubt, if they were able to formulate a religion, they would depict the devil in human form.
Yeah, thank you. It's a long proposition. I really appreciate that you put this one in your thesis. However, in my opinion, it's still an anthropocentric proposition. Do you agree with me?
Yes.
Yes?
I agree.
Yeah. Because, should the emphasis, should I be glad that the emphasis is on were able to formulate a religion, because religion is a human thing, I would say.
Esteemed opponent, thank you for this challenging question. My issue is, with this proposition, what I actually wanted to express is that we should be grateful for the animal research that we are doing, and also that the animals that we use in research, they should be treated with respect.
Absolutely, yeah.
And this is more or less in a way to say only a small thank you to the animals that I have used within my PhD, and actually within these years have passed through my hand. Yes.
Okay. Yeah. We can discuss this further, but I 1000% agree to this. So thank you for that. Then I would like to go to chapter 5 and discuss further on pentixaphore, which is not a surprise to you, I think. When I look at page 131, figure 4, there I indeed see that there is uptake in the early stage, in the more advanced stage. Though, as also some of my previous opponents, what are you really targeting there? That's still the question. And you say macrophages, but might there be also another process that you are targeting? Because this compound is coming from tumor biology. It's used to image cancer. So might there also be another process that you are targeting over here?
Yep. Thank you for this question. Sadly, I'm not exactly sure what you're referring to.
Yeah, I was thinking about hypoxia, because in hypoxia you see that CXCL12 is overexpressed and that you have their CXCL4 expressing cells attracting to that. Mm-hmm. So could it be a hypoxia that you're seeing there as well, or?
At least in the preclinical scenario for mice, so I didn't look specifically into this. Mm-hmm. However, a gut feeling would tell me no, because as far as I know, the vessels from the vessel wall of mice, they do not have capillaries in them. Actually, the entire vessel wall is fed via simple diffusion. So in this case, I would be a little bit reluctant to say that there is hypoxia in a tissue that more or less is not foreseen with capillaries from the start. I cannot guarantee 100% that I am right.
No. But you already mentioned before that you want to do the staining for the macrophages, but it might be a good idea to use pimonidazole as well to check this.
Mm-hmm. Thank you for the tip.
Yeah, you're welcome. Another question. In some previous studies here in this institute, we also checked for overexpression, and we checked the mRNA expression of chemokine receptors in the vulnerable and the stable plaque. Might it be an idea to have this done before you started with the CXCR4 targeting? Because I know that CCR5 is really overexpressed in macrophage-rich plaques. Would that be an alternative, targeting plaques with RANTES or a derivative of RANTES?
Yes, indeed. This would be an alternative. Actually, when I started my PhD, we started with a palette of 4 tracers, two targeting inflammation in completely different ways, and 2 targeting micro-calcification. And these 2 tracers, they showed good uptake inside a vessel wall of animals. However, there's nothing to be excluded that also other tracers, especially as you mentioned, RANTES, would be a good targeting agent for inflamed plaques.
Yeah. So we can go on with RANTES optimization. Yeah. To come back to some topics that have been discussed already here today is you want to detect the vulnerable plaque as early as possible. Is it then a good strategy to target chemokine receptors, or is it also possible to target the chemokines themselves so that you target the inflamed endothelium? Have you thought about that, and what would be a strategy to use here?
To be completely honest, no, I didn't thought up until now about this. However, I'm pretty sure that there are also tracers targeting for interleukins and other cytokines.
Yeah, because it's a very redundant system, all the chemokines and the chemokine receptors. So, I was wondering what your thoughts are about that. Is it possible to target the chemokine itself, or do you think, well, that's a no-go? You shouldn't do this.
I think it would be possible. I think that initial preclinical results may be limited because of also, we're talking here about very small sizes. So it could be that at one point we're reaching a certain threshold that where at least our current preclinical imaging devices are not able to see at all. However, I would not exclude it.
Okay. Well, I'm very satisfied, and I give the word back to the prorector.
Thank you, Dr. Dijkgraaf. The 6th and last opponent is Dr. Armand Jamineau. He is Assistant Professor of Vascular Remodeling and Calcification at Maastricht University. Dr. Jamineau.
Thank you, Paul Rector. Dear candidate, also I would like to congratulate you with this nice piece of work. I read it with much interest, and I also want to take into account my congratulations to the promotion team. So I also want to start off actually with a proposition, and I want to look at proposition 6. So could one of the paronyms please read this proposition?
Proposition 6 is atherosclerosis is an inflammatory disease.
Yes, thank you. So I think as we are already discussing here for quite a while, I think this statement is not really true, or at least it's partly true. Because I mean, if you look at statement 7, and you don't need to read statement 7, you actually disagree with statement 6. So could you maybe, for the clarity, emphasize a bit on how you see the disease atherosclerosis? And I would say that you don't only emphasize on the inflammation part.
Yes, indeed. I put that statement over there because I really like how Ross starts its article from 1992 with this simple sentence, and then then he starts explaining why this it is. Indeed, atherosclerosis is not an exclusive inflammatory disease. However, many processes are happening within the atherosclerotic plaque. Also, micro-calcification is happening, and also fibrosis at one certain degree is also present as a process within the atherosclerotic plaque. However, I think that at least people from the medicine world are would mostly agree only with this statement because it's pretty old. However, yes, I did not mention it that it is an exclusive inflammatory disease.
I think we agree on this statement now, because I think also on the other side, the inflammation part was quite important, right? So I want now to continue to chapter 3, I would expect. And I want to look at page 70, where you show this nice overview of your study. And the first thing I noticed was that you used male mice to study this. Mm-hmm. So my question is, why are you using male mice? Because I think from literature we know mostly that if you look at atherosclerosis at least, you get much more bigger plaques from female mice. Mm-hmm. So my question is, why did you choose for male mice?
Yep. I chose the exclusively male mice within my study for as the female animals, they also have the estrous cycle, which also influences how atherosclerosis is developed. And what I wanted to have within the study is at least try to control the size of the plaques that these animals were developing in order to have a certain degree of control, so that the early stage animals would develop consistently early stage plaques, and the advanced stage animals would have advanced stage plaques. It could have been that if we used also female animals, that the spread of the plaques would be different, and then we would see that some animals have one intense uptake and some animals have less uptake. Also, this was a conscious choice of using only male mice. Also, if you look in the literature, there are not that many studies that actually use both male and female mice in the context of atherosclerosis. Most research is done on male mice, and as we wanted also the data to be comparable, then we wanted to use the male mice. Indeed, it would be an interesting thing actually to use males and female animals.
That's a point which is, I think, very important at this stage, right? I mean, I think the comparison between males and females is nowadays a hot topic, and I think it's very interesting to look at. Yeah. I will quickly continue, because I think you use mice on a diet and you call them early stage lesions. What was the timing again of that? That was.
So for the early stage animals, I also wanted to have the animals the exact same age when I was imaging them. So in the case of the early stage animals, they are for 12 weeks on a Western type diet.
Yes, okay, but so you call them early stage lesions.
Yes.
But they sometimes contain a little of calcified stuff in there, right? So for me, that is not an early lesion, to be honest. So I would reconsider that, calling that at least that is name. For your advanced lesions, I agree they are massively calcified. Although about also definitions, micro-calcification, macro-calcification, that we can have a different debate. But I want to go back to your introduction now. And there you have a nice figure where you show these stages of the plaque. And you show, I think in stage 3, already some calcification spots. And something that you just mentioned while we were discussing here is the vascular smooth muscle cell. So how important is the vascular smooth muscle cell? And are you not forgetting a part of the process when you only look at, I would say now, intimal calcification?
Yes. So the vascular smooth muscle cells are actually the cells that are producing the calcification inside a vessel wall. Indeed, there is also medial calcification, which, at least in a clinical scenario, medial calcification is not necessarily present because of atherosclerosis, however, of a different cardiovascular risk that also the patient possesses, such as diabetes type 2, or diabetes type 1 for that matter, or also a certain degree of CKD, of chronic kidney disease.
Are you aware of the studies which are very ancient from 1944 from Blumenthal et al.? They describe that intimal calcification, or at least intimal remodeling, always is a consequence of medial remodeling. So have you considered looking at the medial layer in your studies?
Yes, I did not exclude also the medial layer, and also within the studies, at least within the dissertation, I specifically chose not to have a difference between intimal and medial calcification, or between the intima and the media.
Mr. Florea, you will have noticed that the time appointed for defending your thesis has passed. The committee will now withdraw to discuss the quality of your thesis, and in particular the quality of your defense today, and please await our return with the results.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the line, I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose that branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Get the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. Even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. South side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and that. Years can't fly by now, don't waste all your time. 'Cause I'll go the extra mile.
Mr. Florea, the degree committee here present has assessed the quality of your thesis and the quality of your defense. And in view of his positive verdict, and of course in taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor, and not such a simple doctor, but you have a double degree of the RWTH Aachen University and Maastricht University. And your promoter, your supervisor, Professor Motaghi, is authorized to confer upon you this academic distinction in accordance with Dutch and German university custom and law. I invite your supervisor now to take the floor. Professor Motaghi.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Alexandru Florea, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with a degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Just some pictures. Okay. Dear Dr. Alex, that's how we will call you now. The first contact I had with Alex was via video conference call after he applied for a position within the IntriCare consortium led by Professor Schürges and Professor Hacking. He presented himself very well structured and was on top of the research he had performed with IMCAR in Aachen, and he was, as also today, he was very self-confident that he could perform everything he wanted from him. So he was really proposed by one of his promoters of his MD master thesis, or MD thesis, Elina Lien at the IMCAR in Aachen, where he had worked several summers during his medical studies already, so he knew Aachen beforehand, before he came to Aachen for his PhD. And we were not really disappointed at no time that he joined our team. He really immediately convinced us after his presentation. And just let me give you a very brief example, and you can all read it in his book, on how precise he is and detailed. As you can see in the first sentence of his CV in its PhD, he added also the weekday of his birthday. So it's quite uncommon, but I thought it's very nice that you added Wednesday. So, and I think that's how you are. So you always are very precise, to the point, not missing a single aspect, and that's certainly a very, very important aspect. And what I would like to say then is his detailed description of processes is really of great value in the research he has been performing and we have seen today. He was also a great help in reorganizing and writing down the quality management protocols and SOPs for our preclinical lab. So next to his own PhD, he also looked at the processes are really standardized, and I think that was an important aspect. And what I would also like to add is that he's a fast learner, very keen to learn all different steps of the preclinical experiments he had performed during his PhD thesis. And due to this, also his social capabilities are very well seen, and he's a very social person. He became one of the main contact persons for the other PhD students in the lab, and this is also reflected in several co-authorships during the time he was a PhD student. I can say he's now one of the pillars in my lab, and I'm happy to have him as a postdoc. Of course, this sounds strange because today is just your PhD defense, but more or less since 1 year, you're already working like a postdoc in my department. His kind, calm, unagitated way of interaction is very well perceived, and I think that's also important in the interaction with the other people. At the same time, he's clear in setting the rules and ask all colleagues to obey, and you can answer this. Yes, the colleagues are sitting there. To obey them, a very important aspect in a lab where several people work. When about ask something, you can always expect a profound and well-structured response, as we have seen also today. He got even the nickname Professor Alex, which is in this sense a future title he will most likely obtain or achieve. Alex has found a very good mixture of work-life balance on the other side. So he's also with the family, he's a family man as far as I can judge. And he's a connoisseur of eating. He loves eating, also at the Weihnachtsmarkt, I learned in Aachen, and enjoyed good drinks, among which egg liquor or advocaat and whiskey. I learned that he loves gardening, so it's also written in the book, but I knew it before. I haven't seen photos, but I know that you love gardening. And he was able to rent a small garden, I think 1 year ago or 2 years ago, I don't know, exactly 2 years ago. It's 1 year, okay. But you already experienced a lot of things, so you talked a lot about it. And he grows all different kind of fruits and vegetables and what else can be grown. I don't know what you, and you have even a cat that is sometimes in the garden, right? So, and here your fancy Anna is certainly a very important person that gives you also the idea on not only what you have to grow in the garden, but also what you have to eat. And you have to give back what you have eaten at the university restaurant. Yeah? So that, I also thought that's a very funny thing, but still, yeah, that's good. So it's always a life-work balance, as I said. So it is a pleasure working with you, and I'm looking really forward for some more common projects on the one side. And you have now started as a physician researcher within our department in Aachen for 1 year, and then after this you will also go into clinics. So maybe some of the questions today that were about clinics, after 3-4 years you will explain them and they will really understand what is about the clinics. So that will be an important aspect. And what I would like to ask you, keep your eagerness to learn, and at the same time your great support for the people surrounding you. That's certainly an important aspect. And with my final words, I would like to wish you, your family, of course, and also your friends, the best. Enjoy your success, and I guess a lot more will come in the future. That's certainly an important aspect, and certainly for today, you have to take the time and really enjoy your second degree that you achieved. Congratulations, Alex.
Thank you.
Esteemed Dr. Florea, dear Alexandru, it is my pleasure to congratulate you with your double doctorate that you have acquired today, and I do that also on behalf of the Board of Deans of Maastricht University, and I think also of the leaders of the RWTH Aachen University as well. Of course, I would like to share some impressions of the committee with you. Well, we have seen a very clear and comprehensive presentation. Excellent, also for lay people. We could understand, but I think that many people in the audience also could understand the summary of your work. Your thesis was well written, and the committee members have read it with pleasure. It's of very good quality, and also part of it has been already well published. We saw a very clear defense, in a few words, impressing, convincing, and self-confident. And, well, it has been said that you really know where you are talking about. You are very knowledgeable about not only the mechanistic, but also other basic elements of your studies, and we are sure that the clinical overview will soon follow and will be more deepened in the near future. In short, the committee is very satisfied with your defense. I would like to include in my congratulations your partner and your family, sitting on the first row, and also your friends and colleagues here present, but also maybe present in the live stream. Congratulations with this result. And of course, I would like to specifically congratulate the 4 supervisors. First of all, Professor Motagi as the main supervisor, and the other 3 supervisors, Professor Kooi, Professor Schurgers, and Professor Bucerius. Congratulations with it fantastic and beautiful result that we have seen today in defense and in the thesis. I would like to thank all the members of both committees, not only this degree committee, but also the thesis assessment committee, and in particular, of course, the external members of the committee. Thank you very much for your input and your presence here today. I would like to say that before I close this ceremony, I would like to give the opportunity to Professor Kiesling, who is present online, and it is my pleasure to give you the opportunity to congratulate the young doctor.
Thank you very much. It's really unfortunate that I don't have the chance to celebrate with you the glass of wine or port wine or sect or whatever. But I would like to congratulate you one more time heartily to this great thesis, but also to this very well done defense that we heard today and your profound answering to the questions. And I find your work particularly impressive, considering that a lot of the work was also done during COVID time, where everything was in lockdown. And in the internal committee meeting, it was said that you are a team player, and I know you also from other research projects, and I can only confirm that. And I think team play is the key. Of science, you are very good to further collaborate with the team and also reading your next publications on your track of becoming a very successful scientist or even a professor. Thank you very much.
Thank you very much, Professor Kiesling. Before I close this ceremony, I would like to invite all people present here to join us with the reception. It's in the rafter, but for now, when the ceremony is closed, please stay here, and we will have first a picture taken here with the committee when Professor Kiesling is still on the screen, and then we will make another picture in the stairs of the hall. So we make a few more pictures than only here. And again, I invite you to go with us afterwards to the reception in the rafter within this building. Hereby I close this academic ceremony.
We keep it right.
If you go with your 2 Paralympians and sit in front of us. Ja, maar Ries staat iets te groot voor. Ja, Ries moet helemaal achteraan. Ries moet achteraan staan.